Welcome to today's video. Today we're going to solve what was an exam, the first year General Relativity. People liked this exercise a lot, and because of that I decided it could be a good exercise to show you how to do related to orbital mechanics. Now this exercise is inspired by an episode of PHYS Spacetime. Very nice YouTube series if you want to watch it. Really cool stuff. Now, in that series they propose a problem like that, which is who will win a race? Somebody going in an orbit like this, or somebody in what is a suborbital flight on the surface of the planet, or somebody that jumps through a tunnel, crossing the whole of Earth, right, to the other side of the Earth. Which one will be winning a race? One going like this, or one going like that? All right. So this inspired me to build this final exam, and we're gonna solve this problem fully. No numerics needed, everything analytical. So it's actually easy to solve, to the point that it could be a final exam. All right, so the way I presented it was the following. Imagine we have Einstein and Newton, and they're discussing about who would arrive first. Somebody that jumps down a tunnel to the other side of Earth, or somebody that follows a suborbital flight, so a geodesic, both are geodesic trajectories, suborbital flight following the surface of Earth. So imagine there's no atmosphere, and then you just accelerate like that, you get that speed, you catch a satellite if you want that's going at that speed there, and it takes you there. Which one would be arriving first? Newton would say, oh, we would be arriving at the same time. And indeed, if you do the Newtonian calculation, I leave it as an exercise with Newtonian gravity, it's very easy to see that the amount is the same. It's around 42 minutes, what you would take. And it's the same no matter if you fall down the tunnel, or if you follow this other geodesic trajectories, the orbital trajectory. Basically, you're moving between 2 points at equipotential surfaces, and when you compute what the result is that you take the same amount of time going down the tunnel or going around. Now the question is, when I consider relativity, general relativity, does the answer change? Does somebody win the race? And if so, who does? So in the exam setup, we dressed up, me and my grad students dressed up and did a little bit of a theatrical representation. I'm not gonna do it now, but it looks something like this. Yeah, the theater company that we created temporarily for that 5 minutes representation was called Time Lagrangian Action. and we did a 5-minute theatrical representation before the exam to present it. Now, here's the summary of things. You have Newton and Einstein discussing about who would win, in a way. Einstein is skeptical when Newton said, yeah, of course, they will arrive at the same time. And then Einstein asked, but whose time? And then Newton said, what do you mean whose time? Time, the universal, absolute time. And then Einstein said, I wouldn't be so sure. And then then you hear Stephen Hawking talk, and Stephen Hawking says, oh, you both think you're very clever. I propose you take a bet, which Stephen Hawking usually does. Einstein, take the suborbital flight. Newton, jump down the tunnel. I will time both of you from here at infinity. So Stephen Hawking is far away at infinity, and he's timing them, and they take, Newton takes the tunnel, Einstein takes the suborbital flight. All right. Now, when they go, Nether shows up and says, oh, these guys, they just disappeared. Well, we're not gonna wait until they finish the race to see who wins, right? We can compute it. That's the fun part. And then she looks at the diagram and said, oh, look at all those symmetries. And then Stephen Hawking said, Professor Nether, please don't give them hints. This is, after all, an exam, and I can hear you even from here at infinity. And then Nether says, all right, I won't say anything else. Okay, so good luck, guys, but don't forget to use my theorem. And then she leaves, and the student start answering the question. Now, this is what we're gonna do here. We're gonna solve the problem. We're gonna see who arrives first and how long they take, and how the time that it takes for them to complete the race compares with the Newtonian prediction of the 42 minutes, and by how much it is corrected. So, first of all, we need to understand what is space-time like here. It's certainly spherically symmetric, and that's nice, because stationary is spherically symmetric, and outside that means that I'm going to have the Schwarzschild solution in absence of matter, right? It's a vacuum solution. But what happens inside? Well, what happens inside is that we're going to have solutions that are given by what is called Tolman-Oppenheimer-Volkov equilibrium. Now, Tolman-Oppenheimer-Volkov equilibrium is assuming that the planet is made out of a perfect fluid, because it's easy to model, and that perfect fluid has constant density, to make it easier to model again, and it's at hydrostatic equilibrium. So at the surface, the pressure is 0, because if it were larger than 0, it would expand. If it were less than 0, it would contract. So it's hydrostatic equilibrium, perfect fluid of constant density. That you're gonna solve an exercise in the assignments about. You're gonna find this metric. Here in the exam, I give it to you. The metric for this case, you see that when R is larger or equal than capital R, we get Schwarzschild metric. R is the radius of the planet. And literally, when it's larger, you see that this is Schwarzschild metric. Okay? Now, when it's inside, we get the internal Schwarzschild solution, if you want. And this is made like this. You can tell that there's no singularity here. There's no horizon, because, of course, this R is larger than the Schwarzschild radius. So this thing will never, there's nothing here that breaks down or fails or anything like that. There are no singularities in here, and also the metric is continuous. You can evaluate. I could actually remove this and put it there if I want, because the metric is continuous. Let's see, the exam was divided in several questions, and we're gonna be asking all those questions and then storing useful results. I don't know where, because we may run out of boards, but we're gonna try our best. So we're gonna be answering the different questions and deriving different results. And let's begin from the beginning. First question. All right, the first question is find the killing vectors and conserved quantities associated to time-like geodesics in this spacetime. Okay, that is a very easy question, because we see that t and phi are both cyclic coordinates. A depends on r, b depends on r. This is r squared, this is r squared sine theta squared. So we don't have any phi's. So we know that we're gonna have two killing vectors. We're gonna have the killing vector k equals partial t, and the killing vector s equal partial phi. If we represent the vectors, so k in the coordinates t, r, theta, phi, k mu is 1, 0, 0, 0, and s mu, it's equal to 0, 0, 0, 1. Right. Now, conserved quantities along time-like geodesics, what we need is to contract the killing vector fields with the four velocities of the objects moving on those time-like trajectories. So we have that the four velocity, let's call it u mu, the four velocities, of course, t dot, so derivative of t with respect to proper time tau, r dot, theta dot, phi dot. So all that we need to compute is the two conserved quantities, E equals k mu u mu, which is equal, of course, to g mu nu k mu u nu. And that gives me, upon substitution, you can substitute, well, here, the k, only the 0, 0 component will contribute because the metric is diagonal, and there are no r, theta, or phi components in k, so we get that this is equal to g tt kt ut, or in other words, this is equal to minus a of r, and then 1, and I won't write, and t dot. All right, so that's the first conserved quantity. Now, how about the second conserved quantity? Well, second conserved quantity, L, is the contraction of S mu with U mu. Same as before, this is G mu nu, S mu, U nu, and of course here there's only phi component, metric is diagonal, so we get phi phi, S phi, U phi, alright, and then upon substitution, G phi phi is r squared sine theta squared, S phi is 1, and U phi is phi dot. So this is the other conserved quantity. All right, so that's the solution to the first exercise. Very simple. So let's store these conserved quantities somewhere over there. So I store the conserved quantities over there, and then the next question. For Einstein's tree for the orbital flight, show that the equation of motion for a time-like orbit in the equatorial plane, theta equals pi over 2, takes the form this from over here. We need to prove that this is the equation of motion. And show that it becomes this very simplified equation of motion that we already found in class for an exterior orbit where the potential, the effective potential, is given by this. Okay, that's not very difficult. So, first of all, we start from the normalization condition for the for velocity. This condition gives me, of course, when I expand it, that's going to be, I'm going to write it here, minus 1 is equal to, and I have minus a of r t dot square, right? Because remember, mu, I'm going to write here, mu is t dot r dot theta dot phi dot, okay? So this is mu t, all right? Then plus b of r dot square, plus, I'm not going to write the rest because the rest are going to be thinking, well, I can write the next one. It would be r square theta dot, well, I'll write all of them, square, plus r square sine theta square phi dot, all right? Square. So this would be the normalization condition. Now I know that this is going to be in the equatorial plane, so this thing is constant. So since theta is constant, the derivative with respect to proper time of theta is 0. And when I have that, I can now plug in, I can substitute, remember, the conserved quantity L. Now in this case, because being this term simplifies, this is a factor of 1, because theta is pi over 2, and also L, it's equal to r squared phi dot. So I can now use this conserved quantity L and this conserved quantity E to eliminate bar phi and T like this, where I used the value, the fact that L is equal to that with pi over 2 for theta, and that E is equal to this. So now I can substitute T dot and phi dot in this equation by the conserved quantities and the coefficients that I found, which gives me this, right? Minus 1 is this one, and then I substitute T dot and phi dot. I get this equation, and very simple algebraic manipulations, this is arithmetics, yields this other equation. And this equation is exactly what I was asked to prove. So, done. Now, also I'm asked to show that it becomes that simple one with this potential for an exterior orbit. Easy. When r is larger than the radius of the planet, then I know that AR is equal to the inverse of BR, you can tell, and equal to this. So, just substituting here, we get directly the response we wanted. And the exercise is done. All right, wonderful. So, next step, next question. All right, the next question is to show that the value of the conserved quantity L squared for a stable circular orbit of radius r is L squared equals to this quantity here. All right, that's not too difficult. We have this potential here. This was, remember, the potential in the equation of motion r dot square equals E minus a potential. So we know that the stable circular orbit would be at the minimum of this potential. All right, so for that, what we do is equate the derivative of this potential to 0. So partial V, partial R equals to 0. And that gives me the following. This equation equated to 0, the derivative of the potential equated to 0, gives me this condition that I can from here solve for L2, L squared, and L squared gives me this expression, which is easy to check that it's a minimum, but just plugging in R on the potential and checking on both sides and saying that it's indeed a minimum. So this gives me the angular momentum related, angular momentum for set component of angular momentum for somebody looking at the orbit from infinity. It gives me the value of this angular momentum in terms of the Schwarzschild radius and the radius of the orbit. This is the Schwarzschild radius, right? If the radius of the orbit is much larger than the Schwarzschild radius, then we find that L squared is approximately, basically you can neglect this term here, all right? So this R cancels one of the R's here. The Schwarzschild radius I can substitute by 2gm, and basically that gives me mgr. And mgr is the value that we obtain for the Newtonian orbit. You remember, for the elliptical orbits, when the eccentricity is 0, is exactly mgr, which is the Newtonian expression for the angular momentum of a circular orbit, angular momentum square for a circular stable orbit in Newtonian mechanics. All right, so next question. All right, so the time has come for us to compute how much time Einstein takes to get from one side of the planet to another. So compute the amount of proper time, delta t e, that it takes Einstein to get from one side of the planet to another. Now also check that in the Newtonian limit, one recovers the Newtonian prediction, which is, by the way, I'll write it here, this is approximately 41.83 minutes, if I remember well. So 42 minutes, more or less. All right, let's get to it. So what we do to solve this is for an equatorial orbit of radius capital R, the conserved quantity L is equal to r squared phi dot. For that I use equation 1 here. And also we got from the previous part equation 2. So I equate that L to the square root of equation 2, of course, here. And that allows me to solve for d phi d tau. And I get this expression. Just substituting, just putting the r on this side and doing a little bit of arithmetic, I get exactly that. From there now, it's very easy to find delta tau Einstein, because delta tau Einstein would be equal, of course, to the integral. So if the origin, if this is the planet, and I call this phi equals 0, then this thing would be phi equals pi. All right. So delta tau E would be equal to the phi from 0 to pi of the tau Einstein d phi. So I substitute the expression, which is the inverse of that one, and I get the following. Integral from 0 to pi d phi, and then I have r times the square root of 2 r rs minus 3. And that integral we can do because nothing depends on phi in here. So this is just pi times r square root of 2 r rs minus 3. Now, we can expand this in a Taylor expansion very easily, given this. So we went a little bit beyond what the exercise was asking. The exercise was telling me, oh, if this thing is actually very large, this ratio is very large, what you have to do is basically neglect the 3. And you get the first term here. But I went one step beyond, and I compute the next term in the series expansion. And you see that this thing is exactly 41.83 minutes. And this thing, this correction, so you see Einstein takes a little bit less than that, but the correction is of the order of around 2 microseconds. You can compute it. The celestial radius of Earth is about 9 millimeters, and the radius of Earth, you know it, is 6,370 more or less kilometers. So it's easy to compute and see that the correction, the relativistic correction in this case, is tiny. So it's mainly the Newtonian prediction, of course, is Earth, right? And a tiny correction of 2 microseconds. But it's kind of cool. Einstein arrives earlier than he would have expected with the Newtonian calculation. All right, let's ask the next question. The next question is to prove that for Einstein's orbit, E squared, the conserved quantity, is equal to this value. And then use this relationship to find how long Einstein took to get to the other side of the planet from the point of view of Stephen Hawking. So let's call this quantity dTE. So the amount of time that Stephen Hawking measured for Einstein trajectory. And it is call it T because Hawking is at infinity and is using flat coordinates T. T, R, theta, phi. Those are the coordinates of Stephen Hawking, who's stationary at infinity. And to solve this exercise, I give you the hint that to recall that this is the equation of motion that we derived. All right, well in this case, what we have to do to find this is remember equation 2. And we can substitute equation 2 in here. But not only that, because the orbit has constant radius, so it's a circular orbit, this implies that r dot is equal to 0. Therefore, doing the two substitutions, r dot equal to 0 and L equals to this, for this circular orbit, we obtain this expression, which what I did is, again, equate r dot to 0, small r equals to capital R, because it's a circular orbit exactly on the surface of the planet. And then we get E squared minus this quantity equal to 0. I just isolate for E, multiply these two things, and what I get is exactly the quantity I was asked to compute. Proven. Now, let's use this to find how long it took for Stephen Hawking. We'll do that finding the relationship between Stephen Hawking's time and the proper time of Einstein. But that's relatively easy because we have the quantity E, and remember that we have that the energy, the E squared quantity is AR squared times T dot square, okay, as we found, I have it here, okay. Then we can substitute this is also equal for this orbit to this quantity, that's why I particularized the capital R, and then what we can do is equate these two expressions. Then AR squared substitute by its expression, which simplifies to this little thing, and remembering that T dot is just dt over d tau Einstein. So with that, I get this equation, d tau Einstein, dt d tau Einstein squared is equal to 2r minus 3 rs, spatial radius. And of course, once that I have this quantity, if I can remove the square and write a square root, and then I know that delta t Einstein would be equal to this quantity, square root, times delta t of proper time Einstein. So the amount of time that Einstein took to get to the other side according to Hawking, it's equal to this redshift factor, let me call it that, times the amount that it took for Einstein. So let's recall what was the amount that it took for Einstein in the previous exercise. Let's just have it here. This is the expression we just obtained in the previous part of the exercise for the amount of proper time that it takes Einstein to get there. Remember, a little bit less than what it takes from the Newtonian prediction. Then let's substitute all the expressions together in here and see what we get for Hawking, which is an interesting result. Okay, we get that. This is the redshift factor. This is the result from Einstein. Okay, so now I could give you the result, but instead of that, I think this is gonna be way more sensational and way more fun if we are surprised together. Let's try to do it, even though my arithmetic sucks. Let's try together. So we have, let's do the product. I'm gonna have the pi r here, and then I'm gonna get the big square root, and that big square root is gonna have, the first term is gonna be 4, and then I have r, I'm gonna write it like this, r over rs, right, like that, and then minus 3, minus 6 r, all right, divided by 2r minus 3rs. All right, so what I can do now, this 6 looks horrible, what I can do now is I can take one r over rs factor outside. Let's do that, because it's gonna be fun. Let's do that. Maybe I'll just do it here. Let's do that one. So I take, I was saying, yeah, I have pi r, and then I have here r over rs outside. So inside the square root, this goes and this replaces with an rs, and look, magic. This is magic. Look, 6rs divided by 2r minus 3rs. Oh my goodness, this is a square root of 2. So what I get as a result in the end is pi r to the 3 over 2 multiplied by the square root of 2 over the Schwarzschild radius. And this, my friends, is the Newtonian prediction. So Stephen Hawking actually measures the Newtonian prediction. When this is Einstein go around the orbit, Stephen Hawking says, all right, yeah, Einstein took the amount of time that Newton predicted, according to me. But although, of course, I knew it, that was Stephen Hawking, right? But still, the point being that it's kind of cool and interesting that Stephen Hawking measures the Newtonian prediction for the orbital flight of Einstein. Even though Einstein measures less than the Newtonian prediction by a couple of microseconds, Stephen Hawking measured exactly the Newtonian prediction. How cool is that? All right, time has come to look into Newton's trip down the tunnel. We almost forget about him. Okay, we move to Newton, and for Newton we have showed that the equations of motion for a time-like fall through the center of the planet are r dot square equals this equation here, and t dot square equals this equation here. Here the dot means, of course, derivative with respect to proper time. In this case, the proper time of Newton, the infalling person. All right, so now, and after that, show that for a particle dropped at radius r equals capital R with 0 velocity, then the conserved quantity E has this magnitude, this value. All right, let's get to it. As usual, to find the equations of motion, what we're going to get is the normalization condition for velocity. All right, we demand that for velocity, of course, is normalized to -1, and same as we did before with Einstein, we obtain the following equations. Now, you need to realize that there's only a t dot and an r dot. There's no theta dot, there's no phi dot. Well, of course, because I'm infalling. So if I'm infalling like that, then theta dot is equal to 0. I'm at the same theta coordinate, and also phi dot is equal to 0. I'm in the equatorial plane, and also I don't move, and this would be the azimuthal angle. As I fall from r to 0, the azimuthal angle is not changing. I'm pointing in the same direction. In this case, it would be 0, right? I'm analyzing only the fall to the center, and then we'll multiply by 2 everything we do. All right, so because theta dot is 0 and phi dot is 0, this is the only part that survives from the for velocity normalization condition. And also, well, the t dot square I can write in terms of E using this equation. Remember, this is universal. We found it without assuming anything. Is the killing conserved quantity along geodesics associated with the cyclic coordinate t. And interesting enough for this case, there's no angular momentum. Of course, if you fall radially, there's no angular momentum. The angular momentum depends on phi dot, and phi dot is 0 because you're in falling radial. All right, so that simplifies things quite a bit. We can substitute the t dot square here by this expression. Let's do that. It's very easy because all that you have to do is evaluate this equation at r equals capital R and time equals 0. So at that time, right, you get that 0 Because E, remember, E is the same at all times. E is a constant of motion in that geodesic. So I can compute it at time equals 0. At time equals 0, small r is capital R, and the derivative is 0 because no initial speed. That's the initial speed, so I just drop it. So 0 is equal to E of, and I get B of capital R, A of capital R, minus 1 B capital R. All right. But if you realize we are at R, so we can take the easy expressions. B and A are inverse to each other at R. So because of that, this thing just tells me that 0 is equal to E minus 1 over BR. And then of course, this is the same, 1 over BR is just AR because they're inverse to each other. So in other words, E is equal to A of capital R, in this case, for the Newton case, the Newton orbit, or the Newton fall. I mean, it's an orbit, but it's an infall, right? And I just substitute, and that thing tells me that E is equal to, so AR is, let me just write from there, 1 minus RS divided by R, because it's evaluated at R, and of course this is the same as this. I can add these two terms, and I get R minus RS divided by R, and there we go, we've proven what we wanted to prove. All right, next question. All right, the time has come for us to ask how long does Newton take in his own proper time to get to the other side of the planet with his radial infall. Now, this is a bit more difficult than in terms of raw calculations than the previous parts. So I gave you helps. First of all, I compiled the time that Einstein took here, both as measured by Einstein in his own proper time and as measured by Stephen Hawking, that actually coincided with the Newtonian prediction. Actually, it made more sense to write the proper time in the Einstein case as the Newtonian one plus a correction, like that, so we can compare all of them. We can write all of them as the Newtonian prediction plus a relativistic correction. So we see that the proper time of Einstein is a little bit less than the Newtonian prediction. As measured by Hawking, though, is exactly the Newtonian prediction. E squared was computed in the previous part by demanding that we just step on the hole with our initial velocity, and because this thing has the same value throughout the whole geodesic, it is the same value as it was originally in the initial time. Now, what I do is I write the equation of motion here, and I substitute E squared by A of AR, right? A of capital R. And now I can integrate directly this equation to get the delta proper time. Notice that I can integrate from 0 to R and multiply by 2 because the path of Newton is from R to 0 and then from 0 to R, and they take the same amount of time to go from the surface to the center, then from the center to the surface again. All right? Now, it's the homogeneity of the planet. Now, this expression here is difficult to integrate, and because of that, I gave you this help. So this is an expansion for a radius that is inside of the planet, and for a planet whose Martial radius is much smaller than the radius of the planet. So think of Earth, 9 millimeters Martial radius, 6,370 kilometers for the radius. So it's certainly, this parameter is very, very, very tiny for Earth. All right, so if you do an expansion, this is the first order term, the second one, and then higher orders. Right, so we substitute that expansion here, and we end up with this expression. Now, these integrals can be done, but I don't want you to waste time trying to do the integrals, so what I did is I gave you this help, the integral solved. All right, so we solved these integrals, and we obtained the following. So substituting the integrals, we obtain that the time that Newton takes in terms of proper time is actually less than the Newtonian prediction, and a little bit less, so it's actually more in terms of proper time than the Einstein prediction, so Newton takes a bit more proper time. But of course, these times are not comparable, they're in different frames, although maybe you can suspect already who's going to win with a clever argument. But you see that Newton also takes less than the Newtonian prediction. All right? Okay, let's store this result here, and let's compute the last thing. So the storing, let's do it right now, like that. And now let's compute what is missing, which is that how much time does it take for Newton to go across the planet from the point of view of Stephen Hawking at infinity. Stephen Hawking is the one who will declare a winner. So let's see. All right, so how long does it take for, according to Stephen Hawking, for Newton to get across the planet? Now, this one is the most difficult one, calculationally speaking. So I gave you more help. I gave you this expansion here, and I also gave you one more integral that we're gonna need. All right, so let's get to it. That is the freaking ink. All right, so what we did is, starting from the equation of motion that we saw at the beginning of starting to compute Newton's trajectory, what we have, this is the derivative of r with respect to proper time, this is the derivative of t with respect to proper time. We can divide the two of them and we obtain the derivative of r with respect to the coordinate time t that corresponds to the proper time of Stephen Hawking. Now this is nice, and by the way, this is a of capital R appears because of e squared, which e squared is a of capital R, and we computed in the parts before, the conserved quantity along the whole geodesic. Now all that we need to do is to integrate the square root of that, or rather the inverse of the square root of that, to get the amount of time that it takes for Newton to get there from one part of the planet to another, and then we do it by multiplying by 2 the amount of time that it takes to go from 0 to r. Okay, we substitute here the inverse of that expression square rooted, and the nice thing is that we get the help. So with the help of the help we expand, and we obtain these integrals that with the help of the help we know also how to compute. After substituting these integrals, the result we get is this. So yeah, the Newtonian prediction plus some more, some small correction of the order of microseconds again. So you see, Newton takes longer than the Newtonian prediction from the point of view of Hawking, and because Einstein took the Newtonian prediction from the point of view of Hawking, we say that Hawking's Newton arrived a little bit later by microseconds than Einstein. So Newton was wrong, even though approximately was right, that they would both take the same time, but he was wrong when you consider relativistic effects. And this problem is non-trivial to deduce when the result is from first principles, from intuition, I would say. In fact, if you come up with a way in which you can actually get the results out of thinking it through, tell me in the live sessions, because I have no freaking clue. This is one of the cases that you have to do the calculations in order to check it. All right, so Stephen Hawking declares a winner, everybody's happy, and with this we end this exercise. This was an exam exercise. In the exam there was way more help. Instead of finding the results, it was actually asked as proof that this is this, so you would not get stuck and you could continue. Everybody got amazing marks in this exam, so as in like the average was actually 85, and the average was skewed toward the distribution was skewed towards the 100, so it was definitely really good results. Anyway, I hope that you had fun with this exercise. It's a fun one and a cute one. I'll see you in the next video where we're gonna see black holes. I'll see you there, and until then, take care.